So very good evening to all the participants. In today's lab session, we are going to implement a recent paper. This is the paper we have shared with you. You can download this data set as well as this paper for your reference, and please upload this data set in your drive. Meanwhile, we'll go ahead with the paper. And if you are unable to upload the data set in your drive because of some internet glitches, we will share it through the collaboratory also so that you can run the code along with us. This is the data set, a novel attention deep neural network assessment method for ECG quality estimation. You can go through the paper. It's a recent paper. So basically what happened to identify the false alarm for any arrhythmia, or you can say other type of cardiovascular diseases, ECG quality estimation can be helpful. So this particular paper that we are going to deploy is based on convolution neural network along with bidirectional LSTM model with dual attentions. One attention is channel-based attention mechanism and one is time-based attention mechanism. So you can go through the paper if you want.
Poornima?
Yes, ma'am.
Because perhaps attention models have not been covered.
Yes.
So may I request the participants to wait for a while? For the moment, let us say that attention is a mechanism that improves the quality of prediction of neural network models. And we will be discussing it in details in the next couple of lectures. So don't worry about it if you do not know what is attention. Attention is a mechanism that helps improve the predictability, or the gives more attention to saliency of the patterns or the information that is available in the data. With that, you can continue. Thank you.
Thank you, ma'am. So we'll start with the objective of the work, that is the quality estimation of ECG signals, and then we will go to the data set part. So I'll explain the data set. Meanwhile, please download this data set, set-a.tar.zz. Please download it. It's a ECG data which is through PhysioNet or CINC Challenge 2011. It has collected the data from 12 lead ECG device, and then the frequency it is ranging is up to 500 hertz. The duration for which it is collecting is 10 seconds, and total 23 volunteers were there who has whose data is used to collect these ECG signals. They have divided the data set in two parts. One is 225 unacceptable or noisy ECG signals, and one is 773 acceptable or acceptable ECG signals. So this is the website. If you want to access the complete data set, you can go through the paper. There is a section, data set present, after the approach, where the link of the data set is given. I'll also paste the link in the chat box. The second section is materials. It has the data set link, and if you want to access it right now, I'm pasting it in the chat box. You can go through the link. They have explained the complete data set, and you can download it directly. It is an open access data set, so you can download this particular data set. It has set A and set B. You can download these data sets. So I'm using this set A, which is used in this particular paper. So you can see there are two classes. One is unacceptable and one is acceptable. But here you can see there is a huge class imbalance problem. 225 are the samples of noisy ECG and 773 are acceptable or non-noisy images, sorry, ECG signals. So if you will plot various data available in the files that we are going to read, you will find out that acceptable signals are like this, and these are unacceptable or noisy signals. So let's start with our lab session and like implementation, and then in between we will go to the approach. What are the steps available to implement that particular paper? So I'm going to my drive. All of you, please go to your drive. So we are in day 9 or wherever you have uploaded the data set, there you have to create a new notebook. So inside practice, I'm uploading the data set. And at the same place, I am creating a new notebook by clicking on this new option. I'm creating a new Google Collaboratory notebook. So I think this step you are doing from very first lab. So you can do it to create a new Google Collaboratory notebook. If you find anything difficult or any issue, please write it in the chat box so that we can help you. So can we start now? All of you are able to upload the data set. Please report it in the chat box. Participants, are you able to upload the data set? Or there is any issue, please tell us. Okay, thank you. So next step is, because the data is in the zip format, you have to unzip. That we will do, and if you are unable to upload it due to some maybe internet glitches, I'm sharing the link of this particular shortcut of this data set so that you can directly access to your drive. So you can open this particular link and then you can add the shortcut in your drive if you don't want to upload it. So this type of window will appear to you when you open the link, and then from here in more action, you will have, let me open it with my other mail. So when you're here, you will find this drive option is there. So when you will click on this add shortcut to drive, it will ask you where you want to save this particular file. So maybe you can save in my drive somewhere. And then you can directly access the data set. So I think now all of you are able to upload the data set, or if you are not able to upload the data set, you can access it through the shared shortcut link. So I'm renaming the file CNN LSTM for ECG quality. First of all, you have to mount your drive. So by clicking on this left menu, that is files, you can mount your drive. So after clicking on this files menu, you have to click on this mount drive option. The third option is mount drive option. Click on this. Then it will ask you for permission to access the Google Drive. So I'm clicking on connect to Google Drive. In my case, drive is mounted. Can you please write in the chat box, are you able to mount or not? Okay, so next is you have to go to the place where you have either uploaded or created the shortcut of the dataset. So in drive, my drive, I'm going to day 9. Inside day 9, practice is the folder where I have uploaded the dataset, the set-a.tar.zz. So I am copying the path of practice folder. Copy path of practice folder, and then I'm changing the current working directory using cd command. Cd space, pasting the path of the folder, not the file. Pasting the path of the folder where we have uploaded the dataset. Just write %cd and then path where you have uploaded the dataset. After that, when you run ls command, you will find out there are 2 files. Extraction is not done. We will go to the extraction now. Now we have just changed the current working directory and checking whether in the current working directory we have the zipped file or not. After that, we will do the extraction. So as explained earlier, this Google Collaboratory provides us background operating system as Linux. So your Linux command will be helpful. Earlier, we have unzipped the .zip or .zip file. This time, in place of .zip, we have tar.zz file. So for that, the command is different. So untar, this is a tar file. So you have to untar it. So for untar, you have to use exclamation mark tar. Tar is a package used in Linux environment. And then because you have to recurrently extract the files, all the files, and you want to display the file names here. So you have to use the parameter as tar space dash. Then you have to provide the parameter as xvzf and then name of the file. Earlier unzip was the file the command you have used. This time you have to use tar dash xvzf and then name of the file. Okay, I'll increase the font size. So I think now it is readable to you all. You have the tar.zz file, then you can directly unzip it using tar dash xvzf, the name of the file. So name of the file is set-a.tar.zz. This is the command that you have to run. Please run it and wait for a while. It will take some time to complete the execution and reflect it to your drive. All of you, please run it. So as you can see, in my case, unzipping or untar is done. Now I am commenting this particular line because no need to untar it next time if you want to rerun the same notebook. So till now it has not reflected in my drive. So now you can see a new folder is created with name as set-a. I'm going inside it. And here you will find out various files are there with different extension. One is .dat, one is .hea, and one is .txt. So .dat or .hear are the file extension that you can use to read it through the MATLAB platform. But for us in like Python based programming, we can directly read it file through .txt, the data through .txt file. All the files have like name are same, but the extension is different. So we are using .txt extension. When you open any of the file, you will find out that there are some 12 columns. The very first is the index, other are the 12 lead ECG signals which has been recorded. So you can check. So we will read only .txt file, not the other two extensions file. Now when I will run ls command, there will be one new folder, that is set-a. If you are done up to this part, please report in the chat box. Either you can write untar or unzip. Please write in the chat box so that we can go ahead. Okay, thank you. So let's see what is there in set-a. ls space name of the folder, that is set-a. Inside set-a, you can see the same file have three different extension .dat, .hea, .txt. So we will read only .txt. And at the end, you will find out this is the header.html. This is a HTML file. When you open, it will be opening in a browser to display the README type of file, the details about the records. These three are the folders, these records, record acceptable, files which has the name of the like all the classes, the acceptable file name. If, for example, if this is the file which is acceptable, this particular record will have the name of the file. Similarly, suppose this is the file which is noisy or unacceptable, the second one, this records dash unacceptable, will have the name of this particular file inside it. So the labels are there inside these two files. Records acceptable, records unacceptable. So we will read the labels from here, and using the corresponding label, we will read the content of the file from after reading the file. Is it clear to you all? Now our next part is reading the data through these files. So as we can see earlier, I have explained you that acceptable and unacceptable records are there in these files. So I am copying this records dash acceptable, and I will open it. I will open this particular file, set-a slash name of the file. And then we will read out how many rows are there. So ACC dot read lines, and then each line we will store in a variable acceptable. And then we will check what is there in acceptable. So you can see it is having the name of the file for acceptable, but each file has some slash n in it. That means slash n is the next line command. And next is, let's check what is the length, because when you will see the paper, there are 773 acceptable records. So as shown to you earlier, these acceptable file names these files have the slash n appended with each file. So what we have to do before reading the data inside the file, we have to remove these slash n. That we will do in the next step. I think instead of going in a higher pace, in between we will take some break so that it will be clear to you all. I'm copying the acceptable data reading file command in the chat box. Please go through it, through which we are reading the file names from records-acceptable file. So it has some 773 file names that we have to read inside acceptable labels. Please run it. And then our next step will be removing that slash n from this particular list. That is acceptable. So what we are doing, we are creating a list, a new empty list, except, sir, because copy is not allowed in the chat box, so you cannot copy it. I'm just pasting it so that if there is any typo error in your file and you are getting any type of issue, so that you can just cross check, because copy paste is disabled, I think, in Zoom. I think so for the current scenario. So we are creating a list, that is an empty list. And then one by one, we will remove the slash n command. Slash n is from each name of the acceptable, this particular list. So for that, because acceptable is a list, you have to go through the list one by one. For that we are using for loop, and we will use enumerate function that will return you the value as well as the index of that particular value. So for data, comma I. So data is the data from acceptable and I is the index. In enumerate and then you have to provide the earlier list. So the data, let me change it. It's I and this is data. I data, and then we will enumerate over acceptable. And then we will append the new data inside accept. So for that, what you have to do? From the data, you have to replace, there is slash n that you have to replace by blank. And then what we can do, we can first check whether it is correct or not. So you can see now there is no slash n, because we have replaced slash n by blank or empty brackets. So these data we have to copy in a new list, that is accept dot append. So this append function, you know that it will be helping you to add the content in a list. And now when you print accept, you will see that now /n is not there in the list. So this is a basic pre-processing that you need, because the same data we are accessing from the actual data set. So whenever you are working with raw data, some type of pre-processing is needed to read the data set. All of you, please run this particular code to access the name of the acceptable files. In the same way, we will now read the content from unacceptable files. Like, first of all, from records acceptable, we have to replace it with records unacceptable, and then we will follow the other steps as followed by these lines. So I'm creating a variable unacceptable, and then we are opening set dash a slash, then I don't have the name of the other file. Let me copy it. It's record unacceptable. I'm copying it and then I'm pasting it over here. So after opening, then we will check how many rows are there. Unacceptable is unacc dot lines, and then length of unacceptable. As we have seen in the paper, or you can go through this slide, there are 225 unacceptable data. Check it whether it is 225 or not. So there are 225 records with unacceptable or noisy signals. When you run the same code for printing unacceptable, you will see it has /n. Our next task is removing this /n. So for that, you have to use the same code like this. Unaccept is the list we are creating, one empty list for I, data that you have to enumerate over the over unacceptable. Then in this particular list, unaccept, you have to append data dot replace, in place of /n, you want to make it empty. Then when you print unaccept, you will see there are 224 data values without /n. You are getting error. There is no object, has no attribute replaced. So please check your for loop. First of all, when you run this code after reading this read lines, you are storing the data in a variable acceptable, which is list. Then you are enumerating over the list. So when you enumerate over the list, it will give you one index and one is the data. I think you have not Hence the variable. I is the index and data is the second one that has the data of that particular index. So I'm waiting for all of you to complete up to this particular part. So this is a basic cleaning, data cleaning process. Now we have name of all the files. So total, I think 773 files are there in acceptable or accept list. This is the list. Accept list has 773 elements in it, which has the name of the acceptable file. Similarly, in this unaccept variable or list, we have 225 elements, which is having the name of the unacceptable files or signals. Now, what you have to do, you have to read the data from these files one by one. Earlier, I have explained, shown you one txt file, which is a quite huge file. When you will go at the end, you will find out that total 5,000 rows are there in a single file. You can see it is starting from 0 and going up to 4,999. So there are total 5,000 rows. So in a single file, there are 5,000 rows. So accordingly, when you read the data from all 773 rows, so it will have the file, the data accordingly. So let's read the data one by one. And another important thing to tell you that the data is there in comma separated file. The file name is .txt, but inside that, if you will see, the data is in comma separated values. So you can use the read CSV function of Panda. So we will use the same. Can we start the data reading process? Or up to this part, anyone is having any issue? So I think there is no issue. I'm going ahead with data reading part because after that we have to do the model building and another part. So I'm using pandas, import pandas as PD, and using PD we will read the text file one by one. So what you will have input and output. So we are creating two variables. One is input and one is output. Two lists we are creating. In input, you will have the data, and output, you will have the label. So first of all, let's read the data from this accept variable. So what we will do, we will read the file name one by one from accept list, and then inside the list, we will read the record that will have 5,000 rows. So the size will be 773, comma 5,000, comma I think 12, because there are 12 ECG signals which we are working with. So for file name in accept, pd.read CSV, and then inside set -a, you have the file name, but you don't have the extension. So I'm appending file name through variable and then appending it with txt, because you have to only read the txt file and you don't have to read the header. So I'm setting header as none. Otherwise, it will treat the first row as header. And I'm storing it in a local variable data. So let me tell you what we need. That there should be, the size should be 773 rows with 5,000. The second index will be 5,000 and then 12. These are the subjects. This is a single entry in a single file and 12 is the feature size. So for that, what you have to do, accordingly, you have to append the data inside this input file. So input dot append from data. We have to access only values. Inside values, all the rows. And earlier we have explained you that when you open the text file, the very first column is index. You can see 0, 1, 2, 3. So no need to access the index. So we are, instead of 0th index, we will start with index 1 and up to index 12 we will go. From 0 to 12, that is total 13 columns were there. So we will read from 1st to 12. In the output, what you have to append? You know the class. It is except. So what you can do, you can like manually do that. That except is first, and for unacceptable, we are using 0. I think one-hot encoding you have earlier used in CNN and segmentation class. Anyone with the issue in one-hot encoding? Do you know how to encode these variables using one-hot encoding? Participants, shall I have to explain one-hot encoding to you? Okay. So what happened? Suppose you have 10 classes. So the output label of that particular data, for that you have to do labeling, will have a size 10. For 10 classes, the size will be 10 and the object is belonging to whichever class, that particular label will be 1, other will be 0. So for example, here we have 2 classes. Number of classes are 2. So the size of label will be 2. That is a list with 0, 0. Currently it is 0, 0. For example, one record X is from except. So for X, the label will be, for except we are writing 1. So that means 0 will be as it is, it will be 1. For example, suppose X2 is from unacceptable. Then the corresponding label will be 1, 0. I think it is clear to you all. So because we are currently reading acceptable files, so our label will be 0, 1. So this is because of one-hot encoding. In place of 2 classes, if you will have 5 classes, and from here you will have 0, then 1 more, 2 more zeros. So it will have 5 class data. Whichever class is true, for that, the label will be 1. So in output, we are going to append 0, 1. So let me run this code and then we will check the length of input and then length of output. Both the lengths should be same. Now I am pasting the code in the chat box. Please run it. Meanwhile, I'll wait for your response. I know it's like little tricky and taking a lot of time of reading the data, but whenever you are working with text data or any other type of numeric other data than numeric data, then it will take some time to data reading and pre-processing. In place of this ECG quality estimation, suppose you are working on in maybe stock market prediction or any other NLP based task, then the pre-processing takes most of the time, maybe 60 to 70% of the time you have to devote to data reading and pre-processing. Please run this particular code, and now we have to run one more code to read unacceptable files data. And then we are good to go to create the model. First of all, we will create the model of the paper given and whatever they have explained in the paper. And then we will try to make some changes. So here the for loop is reading the data from this particular list, except is the list to which we are reading one by one data in file name variable. And then because file name is having the name of the file, which is having the acceptable records. So by passing the path of that particular file, we are reading the data inside a data variable. And then data is a data frame. You know how to work with data frames from very first or second day you are working with pandas and data frames. So to directly access the values from data frame, what we are doing, we are writing the name of the data frame dot values, all the rows, colon is for all the rows, and then comma. Instead of starting with index 0, that is having the indexing 0, 1, 2 up to 4,999, we are starting with 1. And here in the output, what we are doing, we are creating one hot encoding for the label. Here the first index represents unacceptable signals, and the second index, that is index 1, represents the acceptable signals. So this is for acceptable. Now we have to read the unacceptable data also in the same variable, input and output. So this time I'm not creating new list, otherwise it will overwrite. I'm just copying this code. Like we have to copy the code for unacceptable. And in place of accept, I will use unaccept. We have the file name, and then label will be changing this time. In place of 0, 1, now it will be 1, 0, because this time we are reading the other, the second label file, that is unacceptable or noisy. Again, I have pasted the code. There are very slight variation. Only you have to change the accept to unaccept, and then in the output, in place of label 0, 1, you have to use 1, 0. This time when you check the count, it will be 998, because now your list is having both acceptable and unacceptable data. So let's go ahead with changing the data type from list to NumPy array. We have changed the label because for the first, like acceptable signal, the label will be for index 1. It should be true, like the data belongs to index 1 or acceptable. So that's why 1. Unacceptable is index 0. So that's why 1 is here. For third class, if your data is from third class, then 0, 0, 1 will be the label for the that particular data type. So this is a one-hot encoding technique. Next is we have to convert these input and output list to NumPy array. So import NumPy is NP, then NP input is NP.array, pass input, and similarly output is equal to NP.array, pass output. And when you check the shape, input.shape, you will find out it will be having 998, 5000, 12. So this was our basic motive while creating the or reading the data in a proper manner. I think this is clear to you all. Up to this part, if anyone is having any issue, please let us know. Then we will go ahead with the data splitting and then model building part. Any issue till this part, please ask. Okay, so I think there is no issue. I'm going to the paper. When you will read this particular paper completely, you will find out that they have okay. So what they have done, we have randomly chosen 80% of the data for training. That means 80% of the data are for training, 10% is for selecting the model. That means validation, and rest 10% is for testing the model. So accordingly, we will also split the data.
Some
So, sir,
questions, Poornima?
Yes, ma'am.
Why converting data frame to NP?
Yes, ma'am. So this, first of all, this is not a data frame. It is a list. Because when you are using append, that means you are working with list. Earlier, we have created the empty list and then we have appended the data. And the second thing is why we are converting the data into NumPy array, because when you directly run this, if you want to check whether your data pre-processing and data size is correct or not, fit in a model for training, so you have to check the shape. What we need, the first index should contain the number of files, because we have total 998 files, 773 and 225 for acceptable and unacceptable. Each file has 5000 rows and there are 12 columns. So if you read the data properly, this should be the format of your data. So that's why we are converting it to NumPy. First reason is this, and second reason is now we have to split the data into training and testing, and then you have to pass the data to model training. So most of the time you have to pass the data in the form of NumPy array. So let's split the data for training and testing. For splitting the data in training and testing, we will use sklearn's train test split function. So from sklearn dot model selection, we will import this package you are using from earlier labs, train test split function, and then we will call the train test split function. You have to pass, first is input, second is output, and then you have to tell the test size. So we are setting 0.2. That means 20% for testing. Random state, you can set any number, any integer value. Seed, random state, both are same. You have to provide a random integer value. On the basis of that particular value, your randomization will be performed. The other one is, you can see it is suggesting many options. The other one is the shuffle parameter. You can see the shuffle is by default true. So we have to use shuffle true, because in the list you have appended the unacceptable at the end. So there are chances that when you split the data 80% for training and 20% for testing and validation, the acceptable will go to the training only. So that's why shuffle should be true. Now this input will give you two variables. One is, let's say, X train, and one is X test and well. Similarly, Y train and Y test and well from output. These two variables are by splitting your input. When you split output, these two variables will be there. I think Y train and Y test well will be there. So this is the first part. Now what you have to do, from this test well, 50% will be for testing. So it will take your X test well as input, Y test well as input. This time your test size will be 0.5 because you have to divide 50-50 for testing and validation. So Y test, sorry, X test, X well, Y test and Y well. Other parameter we are setting same. So this is the way through which you can split your data. So X train dot shape. It will be having 798 rows or 798 files or records for training. In validation, you will be having 100 records, and for testing, you will be having some 100 records. All of you, please run this particular part. Then we will move to the model building part. Participants, if there is any issue till this part, please let us know. So next is, when you go to this particular research paper, you will find out that what they have done. They have created this particular DAC, that is dual attention LSTM model. What they have done, they have first of all read the data from challenge 2011. So this part is done, this 12 ECG signal. Next is feature engineering. So what they have done, they have initially passed the data to channel-based attention mechanism, followed by convolution layer, then by LSTM and time-based attention mechanism. The output of time-based attention mechanism is passed to a fully connected layer, followed by a softmax classifier. So the same manner we will deploy the code. So this is the structure of channel-based attention mechanism. These images are from the paper itself. For channel-based attention mechanism, what it is doing, it is taking the input of size 5000 cross 12 that you have. It is passing the code data to average pooling layer or you can say global average pooling layer, it is passing the data. That is converting your data. In place of 5,000 cross 12, it will be 1 cross 12. Okay? Averaging the data for these 5,000 data points. Then a dense layer is there, or you can say fully connected layer is there. The output is 3. That means in the fully connected layer, you will be having 3 neurons. That's why the output is 3. Again, it is passing to a fully connected layer, which because the output is 12, that means you are having the 12 neurons in the other layer. And then the output is passed to a sigmoid layer. And then the input is multiplied to the output of the sigmoid. So this is the structure of your channel-based attention module. For time-based attention module, what they have done, here they have passed the data to 10H activation function. And then from 10H, they have passed the data to softmax layer, that is softmax activation function, and then multiply the input to the output. So this is the structure of time-based attention. We have to deploy these two attention mechanism, and this is the complete structure that you have to deploy. So one by one, we will try to cover this particular implementation, and then we will check the performance. Another important thing to tell you is that as per the paper, they have not performed any type of normalization. But if time permits, we will try to first of all do the normalization and then run the same model to check what is the performance changes that we are getting. They have not converted the data into like in between -1 to 1 to normalize earlier that we have done. So because of the paper, we are not doing that part, but we can try that. So let's go ahead with the implementation. First of all, you have to create one input layer. So from any one of you can tell what will be the size of your input. Suppose we have 798 records, each of size 5,000 cross 12. So what will be the size of your input layer? What will be size of your single record? That will be size of your input layer. So as we are going to use Keras, I'm importing TensorFlow. Meanwhile, you can write the answer in the chat box. What will be the size of your input layer? So from tf.keras.layers, we are using input layer. You can write input layer or self, like only input can be also used. So in input, you have to pass the shape. What will be the shape or input shape? It will be 5,000 cross 12. That is the size of single record. So whatever will be the size of single record, that will be the input to your model. For example, in images, if your input size is 224 cross 224 cross 3 for one image, so the shape is 224, 224, 3. So accordingly, here we have single record of 5,000 cross 12. So shape is 5,000 cross 12. So this is our input layer. Next layer is channel-based attention mechanism. So this is the complete block. I'm creating a function separately for channel attention. That will be taking the input from this particular layer. Input will be passed to here. The very first layer of this is fully connected sorry, I think not fully connected layer. They have given global average. Yes, you can see average pooling layer is there. So what you have to do, you have to use average pooling layer. Global average pooling layer will be there. But our data is in 2 dimension. You can see 5000 cross 12. So in place earlier in CNN, you have used con 2D, global average pooling 2D, or max pooling 2D. So when you are working with images, that is 3 dimension, and that is height, width, and channels. There you are using con 2D, con 3D, max pooling 2D. But here our data is 2 dimension. The signal data is in 2 dimension. So that's why we will use 1D, 1 dimension functions are there. So from tf.keras.layers, we will use average pooling 1D. So your input data will be passed to this particular layer. I'm creating the variable average. Then the next layer is fully connected layer with output as 3. And similarly, fully connected layer. This is again W1 X1 plus B. That is, this Y1 is the output of this. That is again a dense layer with output as 12. So we will use dense 1 tf.keras.layers dot dense it is having 3 as output. So number of neurons here will be 3. The activation function they have not defined, but if you want, you can use ReLU. I'm using ReLU. In the paper, it is not written. And then I'm passing average from here to here. Similarly, I'm creating dense 2 tf.keras.layers.dense. This time the output is 12, so I'm writing 12 here. Activation is ReLU, and it will be having dense 1 as input. The next is sigmoid. So sigmoid is equal to tf.keras. This in place of layers, we have to access it from the activations. Activations dot sigmoid, and there you have to pass dense 2. And at the end, you have to multiply. So from TensorFlow.keras.layers, you have to use multiply. And it will be taking 2 inputs. Your input data followed by output of sigmoid. And this is your final output of channel attention that you have to return. I will paste the code in the chat box when the model will be successfully compiled. Because currently I'm writing the code, so there are chances that there may be some typo or any other type of error. So we have created channel attention module. So I'm calling this channel attention module that will be taking input as input layer. Then you will go to the model. You will see the next is convolution layers. Various convolution layers are available with size 5 as kernel in initial 2 layers. Other 3 layers will be having the kernel sizes 2. So we have to create 5 convolution layers. And then you can see this table 1 is reflecting that what will be the output. So what we have done, we have compared this number of output to like create what will be the number of filters. For example, in con1, kernel size is 5, stride is 5, and the number of output, like what the output of convolution, first convolution is 1000 cross 16. So this 1000 will be, because we are using stride as 5, and this 16 will be the number of filters. We will use 16 filters. So that's why 16. Similarly, in the second one, again, the stride is 5. So in CNN part, you have understood that how to work with stride. So the output will be 200. The number of filters we will use are 32. Similarly, in the third one, 2 will be the kernel size, stride will be 2. Number of filters will be 64. In the fourth convolution layer, 2 will be the kernel size, 2 will be the stride, and 64 will be the number of filters. Similarly with the fifth convolution layer. So these 5 convolution layers now we will create. I'm using con1 tf.cares.layers. And then because your data is in row column format, there is no channel. So con1d. Con1d. Similar to con2d, here also you have to define the number of filters. Number of filters in the first is 16. You can see 16 is the output. So that's why number of filters will be 16. In strides is again stride is given to you. This is 5, and then kernel size you have to define. You can change the position of your parameters according to your convenience. I'm using you can use kernel size before filters or after filters also. So kernel size is 5. Then activation we will use, that is ReLU. And then for a meanwhile, I'm closing the chat box. After completing the code, I'll read the comment from the chat box. The output of channel attention, I am pasting to or passing the output to input to first convolution layer. Input. Next is the second convolution layer. As we have seen in the paper, in the second convolution layer, the kernel size and filter size stride is same, but number of filters are 32. So in place of 16, we will have 32, and output of first convolution will be the input to the second convolution. Similarly, now we have to create 3 more layers, but this time kernel size and stride will be changing. And then all the 3 layers will be having 64 number of filters. So this will be con3. Number of filters will be 64. Stride will be 2. Kernel size will be 2. And con2 will be the input to con3. Now con4 and 5. This is con4 and 5. Number of filters are same. Stride and kernel size are again same. But it will be having input from con3 and it will be having the input from con4. So this is the structure from convolution model. Input layer followed by channel attention followed by 5 convolution layer till this part. Now you have to create the other attention module, that is this time-based attention mechanism. Before that, we have by LSTM. Sorry, I forget to add one more layer, that is by LSTM. Before time-based attention, we have to add by LSTM. So this is from RNN part, that is bidirectional LSTM module. You have studied LSTM today. So when your model work in both the directions, that is bidirectional LSTM model. In TensorFlow or Keras, the bidirectional LSTM is already implemented. So we are using the same. If you want to improve the performance of this particular paper, you can try with other combination and you can work on the same paper. So from tf.cares.layers, what you have to use? You have to use bidirectional LSTM. So from layers, you have to use bidirectional. And this you have to pass to LSTM, tf.cares.layers.lstm. Similarly, you can, in place of LSTM, you can write GRU to access the GRU unit. So as per the paper, you will see that it is having 128 features. You can see, let me show you. I think this 128 kernel size dense. So 128 is there. So if I will use 128 currently here, let me tell you, number of units are 128, then what will be the changes? And then accordingly, you have to adjust these. And then input to your bidirectional LSTM layer will be con 5. So this is our bidirectional LSTM layer. After that, time-based attention is there. So these are the layers. You have to create 10H and then softmax. So let me create another function for time-based attention mechanism. Define time attention. It will be having input data. So the very first is the 10H and then softmax. So from tensorflow.cares.layers, we will using 10H. Sorry, this is activation function. So from tensorflow.cares.activation, activations, we have to use 10H. That will be having input data. Here is input. And then you have to pass it to softmax. So tf.cares.activations.softmax and 10H will be there. And then next is you have to multiply. So from tf.cares.layers.multiply, you have to multiply your input data with the softmax output. And then you have to return it. So this is our output of time attention, time-based attention. And then we will return it. After the bidirectional LSTM layer, you have to use this time-based attention. The input to this will be bidirectional LSTM. So this is our time attention. Now after the time attention module, some dense layers are there. You can see dense layer with 64. 64 is the output. That means 64 neurons will be there in the dense layer. So dense 1 will be tf.cares.layers.dense 64. Activation will be ReLU here. And then input to this particular dense layer will be time output of the time-based attention. And then you will be having the output. This is the output layer, which will be having 2 neurons because you have 2 classes. One is acceptable, one is unacceptable. So output is df.chars.layers.dense 2, comma, activation will be this time softmax. And then input to the output layer will be dense 1. Now we have created a graph of the various layers. Next is you have to create the model. So this is a functional API based model that we are creating. Earlier we have worked with the sequential model. So to create the functional API based model, what you have to call tf.rs.models. For calling the sequential model, you have to write sequential, but we are in place of sequential, you have to use this model. You can see sequential is one type of model. This model is the other one, that is functional API based model. It takes the basic 2 parameter. The very first is the input, that is this variable we have created. And then second is the outputs. Why inputs and outputs? Because it can even work with multiple input, multiple output neural network. And then this is our CNN LSTM model. If everything goes well, it will plot the summary. Then there is a slight change that we have to make. Let me run it again. Okay. So in place of average pooling, you have to use global average pooling. That will be converting it into 5000 cross 12. Bidirectional, there is some spelling mistake. So that's why I have not copied the code earlier and pasted it into the chat box so that at the end, the output will be correct. So you can see in the bidirectional layer, the output shape is 256. But when you will see the documentation, it is 128. So that means if you will write 128, because it is a bidirectional LSTM, it will double the number of units in the LSTM, number of hidden units. So I will be using 64 here so that it will be having output as 128. So this time the output is 128. Now I am pasting the code in the chat box. The very first is the channel attention code. The second is time attention code. And then third one is the complete model code. I'm giving you 2 minutes time. It's 7:24. At 7:26, we will then go ahead. Meanwhile, if you have any issue, please let us know in the chat box. Please run this particular code. Compare the code with the paper if you have time. And if you are finding any issue, please let us know. We will start at 7:26 again to check how to calculate these parameters. Because you cannot read the content from my window. That's why I have copied the code in the chat box so that it will be easier to you to complete the code. Or if you need more time, you can write in the chat box that too. So till this part, we have read the data, pre-process it, and then created the model explained in the research paper. Now the training part is remaining, and then you have to do the evaluation. First of all, we will see how to calculate the parameter. And then we will go ahead with the training and testing part or evaluation part. So participants, are you finding it like difficult or any other issue is there? Because I'm not getting any response.
Please feel free in telling participants we are here just to have a good experience of you for in learning AI ML. In case you are finding it hard, please feel free in telling us. We'll try our best to make it as simple as possible for you.
Definitely you can have like 5 minutes to complete your code. So there is a question in case of 5 classes, what will be the labels? So if you are using one hot encoding, the size of the label will be a list of size 5. 5 elements will be there. Suppose your data belongs to the very first class. So for that particular data, the label will be 1, 4 times 0. Suppose your data belongs to second class. So in the list, the second index will be, or you can say like if you are starting with counting with 0th index, so the first index will be 1, other will be 0. If your data belongs to the last class, that is the 5th class, the last index will be 1, other will be 0. Other initial 4 will be 0. So when you go through the documentation of this particular data set, you'll find out that initially they have divided the data into 3 classes. So you can work on that data also in place of 2 acceptable and acceptable. One more class is also there. Any other issue, participants? So let's go ahead with the parameter calculation to compare the parameters we have in the model. In the input layer, there will be no parameter. Again, in the global average pooling layer, there will be no parameter. Then you have to go inside the channel attention. In channel attention, other than global average pooling layer, 2 dense layers are there in sigmoid and then multiply. So only dense layer will be having the parameters. Sigmoid and multiply will not have the parameter. So first of all, talking about the dense layer. Earlier also you have done this in ANN part. You have done how to calculate the number of parameters. Whatever will be the number of neurons in your input layer or the first hidden layer, or whatever will be the input size of your that particular hidden layer, multiply by the output size of the hidden layer plus output size. So because input size into output size will be the size of the weight matrix plus output size. This is the bias. So accordingly, when you are talking about this particular first dense layer, the input is 12 from global average pooling layer. The input is 12. Multiply by 3, that is 36. And again, for each neuron in the first dense layer, 1 bias will be there. So 3 biases will be there. So 36 plus 3, that is 39 neurons will be, 39 parameters will be there in the dense layer. Again, when talking about the second dense layer, the input is 3, the output is 12. So the weight matrix size will be 3 into 12. And biases will be 12. So number of parameters will be 3 into 12. That is 36 plus 12 bias. So plus 12, that is 48 will be there. Now sigmoid will be having no parameter. Similarly, multiply will also not having any parameter. Now we are going to con 1D. In the earlier classes, when you are working with con 2D, the parameter calculation was little different than here. Because in con 2D, you had channel also. Here we have like, this is 2-dimension rows and columns, or you can say single row and then channel is there in con 1D. So to calculate the number of parameter in the first con 1D, for con 1D, whatever will be the input size, multiply by number of filters plus number of filters. So it is same as dense. Input into number of filters, that means the size of your output, the depth of your output, plus for each filter, there will be one bias. So that's why whatever will be the number of filters, that will be the bias count. But the input size here will be varying little bit because you are having the data in 2 dimensions. So the input size will be, you have to getting the filter size here. I'll explain you how to calculate that. For example, the input to your con 1D is 5000 cross 12. So you can say 12 is the channel. This filter size, or you can say channel output, the channel sizes. Let me start with this. The filter size is 5. Let me open the calculator so that I think, or a Word notebook, so that I can explain you in better way. The filter size is 5, or kernel size is 5. Number of filters are 16. Number of filters are 16. And input is 5000 cross 12. So when calculating the actual input for this particular con layer, when you are calculating the actual input, so the input size will be filter size multiplied by the channel of the input. So we have 12, so 5 into 12. In case of con 1D, when you are working with con 2D, the filter size will be 5 cross 5. This will be the size of the filter. So it will be 5 cross 5 cross 12. Like this, you have to work with con 2D. But for con 2D, it will be 5 cross 12. Whatever will be the channel of last layer or input to this particular layer, whatever will be the channel, that will be your multiply with your number of filter size to get the input size. So to calculate the number of parameters, what you have to do, parameters will be, this is your input size, 5 is the filter, one filter is of size 5 into 12. This is your single filter size, 5 into 12. And there are total 16 filters. So 5 into 12 into 16. And then for each filter, one bias will be there, so 16. Five into 12 is the size of single filter. There are such 16 filter. 960 plus 16 for bias. So 976. You can see 976 is the size of number of parameter in the first convolution layer. Again, in the second convolution layer, kernel size tried is same, filters are 32. So this time, filters are 32. One filter size is 5. So filter size will be 5. And in the previous layer, the channel was 16. So this time their filter will be expanded up to 16. So earlier it was 5 cross 12. Single filter size. But this time you have to expand the filter up to 16 because the output of previous layer was 16. So 5 into 16, single filter size. So total parameters will be single filter size into number of filters. Number of filters are 32. Each filter one bias, so total 32 biases. So 5 into 16 will be the size of single filter. Such 32 filters are there. 2592. So you can see 2592 parameters are there. Similarly, you can calculate for other 3 convolution layers. Now when talking about the bidirectional LSTM, that means LSTM with 2 directions. So in LSTM, first of all, when you calculate the number of parameter in LSTM, it will be the same, because LSTM units are, again, it will be depending on your input size and number of hidden units. So in LSTM, you have 64 units, hidden units. And 64 is the hidden unit. And input to your bidirectional LSTM is again 64. Input is 64. So as per the LSTM parameter, when you are talking about LSTM parameters, so first of all, you have to combine your input with the number of hidden units in LSTM. Number of hidden units are 64 plus input to your input size of your LSTM is again 64. That is 128. Multiply by number of hidden units. Number of hidden units are 64. For each hidden unit, 1 bias. So total 64 biases. And it will be multiplied by 4 for LSTM based on the number of gates and the biases. So let me calculate 128 into 64 plus 64. 8256 and then multiply by 4. So 33024 are the number of parameters in LSTM. And when you are talking about bidirectional LSTM, that means your parameter will be double. So again multiply by 2. So 66048. Let me check it is correct or not. Yes, 66048. So bidirectional LSTM will be having 2 into number of parameter in LSTM. So that's why it is having 66048. Up to this part you have done. Dense, you know how to calculate 128 into 64 plus 64. For this dense, 64 into 2 plus 2. So total parameters are 98,761. I think this is clear to you all to how to calculate the number of parameter in Con 1D and LSTM. Other dense and CN, basic CN and Con 2D, you know. Now your model is ready. Next is you have to compile your model. So for compilation, you have to pass 3 basic parameters, the optimizer, loss, and performance matrix. So model.compile. Loss is because we are using the one hot encoding, so categorical cross entropy loss. If you are using the index value like 0, 1, 2, 3, so then you have to use sparse categorical cross entropy loss. Categorical cross entropy. And then optimizer, as per the paper, they have used Adam. So we are also using Adam. So other parameters or hyperparameters, they have not given. They have not given what is the learning rate. So we are also going with the default learning rate. The third is the performance matrix. The performance matrix, for a while, let's use only accuracy. Later on, you can dive it like precision, recall, Evans scope. And the name of the model is CNN LSTM model. This is the way through which we can compile the model. Next is model training. So I'm storing the data in a variable history. Then we are CNN LSTM model dot fit for training. The very first parameter will be your training data and corresponding output. So training data is X train and corresponding output is Y train. X underscore train, comma Y underscore train. Then you have to use the batch size as per the paper. We have used the batch size as 256. So whatever parameter they have given, we are using the same. Epochs are not given. So for a while, let's use 30. Then you can try with other epochs to check what is the best suitable. They have given the validation data set. So our validation data is X underscore well, comma, Y underscore well. I think this is all for training. I'm pasting the compilation and training code. So we are multiplying the parameter to 4 because as per the, when you will see the structure of LSTM, you'll find out that based on the gates, it's 3. You have 3 gates, it's 4. That's why we are multiplying it with 4. When you go inside the structure of LSTM, you'll find out that your input is first of all combined with your hidden units, and then it is passed to the other gates. So that's why this is the logic. So let me stop the training here. Why I'm stopping? Because you can see there is no change in the accuracy and validation accuracy. So what we can do, optim is equal to tf dot keras dot optimizers dot atom. And this time let me set a learning rate. And I will rerun the code. This time the accuracy is changing. So because they have not given the learning rate and number of epochs. So like we have assumed what could be the possible. And to compare to get the same result, you can try with multiple like learning rate and epochs. It will take some time. And then we will evaluate the model. CNN LSTM model dot evaluate. Then you have to pass X test and then Y test. So you can see we are getting some 79% of accuracy, but you have to try with like other combination also. Like if I will set learning rate. Earlier I was getting 95% of accuracy. you can also achieve the same. Maybe you have to increase the number of epochs and change the learning rate. So up to this part, anyone having any issue? Participants, any issue till this part?
We have some 7-8 minutes, Poornima.
Yes, ma'am. And that's why I'm like about to.
Yeah, it's
conclude.
about to be completed. Yeah.
Yes, ma'am. Are you able to run the complete code? What is the performance you are getting when you are running this evaluate? Can you please write it in the chat box? Last few lines. The compilation and training is done. The evaluate code I have to paste. What is the performance you are getting when you are running this code? Anyone please write. So we have completed the coding of this particular model. Okay, you need the code of optimizer. We have completed the code of this particular model. So the very first scope that we find out that that is possible is to, before passing the data to your model, you have to normalize the data. When you normalize the data, you'll find out that the result are maybe better than the result we are getting right now. The second is that this data set has having 2 classes, so you can work with by increasing the number of classes which is available. The third class is also there. And you can also change the structure of your model. For example, here we are using bidirectional LSTM with single layer you are using. You can increase the number of layers. In place of LSTM, you can use GRU. As explained by ma'am, you can also use GRU for the enhancement or model changing part, or other structures. You can also try without attentions, without these convolution layers. So this time the accuracy is 88.99%. when you are running for 100 epochs. The epochs are not given in the paper, so you have to try with different optimize like learning rate as well as the epochs. So I think this is all for today. Any doubt you have till this part, you can ask in the chat box. Participants, or can we conclude the session for now? So I'm stopping. I'll upload the code in the drive.